turns out that that last rule we proved actually extends to polynomials in general. Okay, as if I have a whole bunch of terms that are of that form, so a constant times x raised to some power. Okay, then I can just apply that same rule term by term by term. Okay, and well, of course, I think there's a typo here. It should be times k. Right? Okay. See, so the exponent comes down, and then you subtract 1 in the exponent, and right. So, all right. So, so just for an example, suppose I have a polynomial like this. This is f of x is 3x to the 5th plus 2x to the negative 4th. That's right. You can have negative exponents. That's fine. Minus 1.2x plus 100,000, or maybe even 100 billion. Why not? Who cares? Then what's the derivative with respect to x of f of x? Now, the rule says bring that exponent down and then subtract 1 from it. For the next term, do the same thing. Bring that exponent down. Negative 4 times 2. That's the 2. You keep these coefficients there. They don't disappear or anything. They stay. Okay. This 5 is this 5. This negative 4 is this negative 4. And then in the top here, I've got to subtract 1. Right? So this becomes negative 5. Okay. Subtract 1. And then minus what happens here. The exponent up here is actually a 1. So you get a 1 comes down times 1.2. Right? And then times x raised to the 0, subtract 1, then plus, what happens to this? It just goes away, 0, because this is really like having an x to the 0 over here, right? So if you bring the 0 down and put it over here, you really get 0, right? Because you're multiplying through by 0. So what does all this stuff come out to be? This will be 15, because 3 times 5 is 15, x to the 4th, minus oops, I'm missing an x over here, isn't it? Okay, minus 8 x to the negative 5th, and then minus 1 times 1.2 is 1.2. X to the 0 is just 1, and there you have it. That's it. Okay, so that power rule just applies to, you can apply it to term by term in polynomials.